It's nice to be here. I want to say that I want to share my story, and my project is focused on continuous time delta sigma integrator with focusing on digital implementation of the blocks. So here is the agenda. As you can see, okay, so the main question is that why do we still analog? So according to the figure that you can see, the analog to digital converter seems to be a crucial blocks, and it's affect the performance of this many systems. For example, in power amplifier, in the transmitter, and also the digital signal processors the analog signal are needed to convert it into the digital. In this case, the high performance ADC demand increases, and here are the three ingredients of every ADC is mentioned: resolution, speed operation, and power, which summarize in one parameter figure of merits, which analyze the performance of the ADC. So in this slides, I want to tell that the analog signal, how we can convert it in digital way, and here is in this slide we want to discuss about the challenges that the analog circuit faces. The first challenge is corresponding to scaling. As you know, in IoT nodes, which is the title of this project, we are looking for a saving area occupation and faster speed operation, power efficiency, and scalable supply voltage. According to the Moore's law, when every 2 years the number of the transistors are going to be doubled, and this scalability of the technology is an inevitable part of the technology, and as the technology is scaled down, the power supply is also decreases, as you can see, and this results in poor analog features. For example, low intrinsic gain, and the SNR degradation, and high relative area. In this case, you are seeing that the unfunny side of scaling, since the analog and digital systems are in this specific case are scaled by a factor of 4, but the analog circuit remains the same in order to maintain the specific performance, but the digital shrinked as well. So in this case, the designer tried to change their policy, and from the cascaded stack and transistor into the folding structure, and using a multiple branch in order to gain their performance within the limited supply voltage. So in this slide, the question is that, is analog circuit better? I want to mention that we have two domains in the electronics: digital, analog, and the digital has many advantages. For example, the power consumption, design simplicity, and test scalability, and robust against PVT variation, noise immunity. But the analog has faced many challenges. for designer, sensitivity to PVT, significant design effort, and time iteration, and the static power consumption, and so on. So in this slide, I want to make comparison between design flow of the digital and analog systems. As you can see, the analog design flow is facing with less systematic way. And in this case, it takes more time and design efforts. And also, on the other hand, the digital has many benefits in this case, in the way that we can synthesize the system in semi-automatic way by means of the hardware description language tools. So the idea is to move toward the digital implementation of the blocks. So as you can see, this is a summary of the previous slide. The analog do not take advantage of a scaling. The power consumption is high due to the static current flow and limited configurability and significant time, cost, and design efforts. So is there any way that we can get rid of analog? I would say no, we cannot get rid of analog, because at least in the interface we have to process analog signals, especially in IoT node, as you can see in this figure. In IoT node, there are many analog signals from pressure, lights, or I don't know. Every analog signals need to conditioned by amplifier, by low-pass filter, or are going to be ready to digital and to be digital by the ADC, which is the integral part of this conversion, and getting ready for signal processing or etc. So the methodology is to implement the analog blocks in digital manner. In recent years, many researchers try to implement the analog blocks, for example, phase lock loop and low dropout voltage, voltage reference, and amplifier. But the ADC implementation is which is the topic of this project, is the topic which is going to be one of the challenges, and the common trend toward to move the functionality of the digital domain increase the interest in ADC. So in this case, since the integral part of the ADC is an amplifier, we try to make a new concept of amplification in digital domain. So in this case, you can see that the simplest analog amplifier with the analog compensation circuits. Why we need the analog compensation? Because we need the output voltage to be constant, balanced, and stable. So any fluctuation in the output stage would be devastating for performance of analog. So in this case, sensing the common mode, comparing the difference applied to the current source is the way that the traditional designer use that by applying the digital negative feedback. So in this case, we substitute the digital logic system to compensate this system, and after that we implement the digital amplifier. which is the inverter-based amplifier, and you can see that the whole system are digitized. So it has two benefits. The first, static power flow. Since in this concept we use the dynamic biasing technique, the current flowing throughout the VDD to ground is minimized, and especially the transistor working in deep subthreshold in order of nano-ampere. And the digital implementation has many benefits and ensure integration, and also in this way we take advantage of lower design time, effort, and cost. So in this slide we want to focus on the digital floating-inverter amplifier. So we use the inverter as a core of the system. The analog signal is applied. The analog signal is applied to these two inverters, super inverters, and as you can see, the amplified signal, which is shown in this figure, is applied to the inverter chain. Inverter chain digitize the signal, amplified signal, and produce the inv plus and minus, which inv plus and minus depending on a logic 0, 0, 1, 1, 1, 0, and 0, 1. 0, 0, and 1, 1 is a common mode compensation, since the output of the inverter is not distinguishable. It means that it's resulted in the same output bits, and the amplification is not performed well. So in this case we need to compensate the circuits by means of applying the common mode compensation system in order to follow the differential states, 0, 1 or 1, 0 states. In the end, and also as you can see, for example, if we are in a 0, 0 state, as you can see in a CMC block, the VCML is connected to the ground, and as a result of that, the VCM, as you can see here, is discharged to reach the specific value, which we call this this voltage or floating, and this is a concept. And according to this methodology, if the circuit can distinguish between their inputs and amplify it well, it follows the 0, 1 or 1, 0 states. It means that by increasing the analog inputs, for example, consider the sine wave, the output is increased, and vice versa. So this is the summary of the benefits if we use the dynamic or static bias topology in our case. In dynamic we have the more complex circuits which modify bias current more efficiently, and it has many benefits over the power consumption and is more adaptable. But the static current, the main constraint is the energy efficiency, and also it can provide the stability and precise control system. So let's go back to the sigma delta modulator. As I said before, the main part of the sigma delta modulator is the integrator, which we wanted to implement it as a digital implementation. As you can see here, we have two parts, analog and digital. So if we implement the integrator in digital manner, we can take advantage of the digital implementation. So this is the a single-ended architecture that we implement in the TSMC technology, but before doing so, we have to be aware about the concept of sigma delta modulator. According to the Nyquist theory, when you want to reconstruct the signal, you have to sample at least the twice of the input signal frequency. This resulted in two main categories in the Nyquist ADC and oversampling ADC. So in this case, if you sample more than bandwidths of the input signal, the in-band noise are spread throughout the wider frequency. And in this case, we decrease the in-band noise magnificently by the ratio of oversampling. And another technique that is used in the sigma delta modulator is the feedback modulation technique, which in this case the idea is to pushing the low frequency component, low frequency noise into the higher frequency by filtering the noise. And in this case, this is necessary to understand. So the first order sigma delta modulator, the question is that is it the possible solution for implementation of the ADC in digital manner. So as you can see, by adding a D flip-flop, you can see that the circuits can work properly, and the DGOTA CMP CMC out is the same as before we mentioned, but we model the architecture in Verilog and use the hardware description language in mixed signal, and this is the flow chart that you can see. We have a two loop, local loop and general loop. The local loop corresponding the common mode compensation mechanisms, and the general loop for closing this system. So in this case, this is the summary of the result compared to the state of art. According to this table, you can see that the power consumption is magnificently efficient in range of nano-Watt compared to other sigma delta modulator, and the FOM is not so good compared to other state-of-art result, but it makes that this concept suitable for IoT nodes, since we need ultra low power, smaller, and more importantly, digitally implemented concept. This is the preliminary result, and also we are going to moving to design and simulate and taping out the higher order sigma delta modulator, and finalizing the scheme. Thank you so much.